Hello everyone, this is Jiangchuan Huang. Today I'm going to present our paper, Cloud Computing in Space. This is joint work with Professor Christoph Kirsch from the University of Salzburg and Professor Raja Sengupta from UC Berkeley. We're very interested in tasks arriving in time and space. So we have K customers and M vehicles. Each customer hosts a sequence of tasks. A task is a three-tuple. It has arrival time, location, and size. To serve a task involving send one of the real vehicles to first travel to the task location and spend some time executing the tasks. The performance metrics include our average waiting time and total distance traveled, or other metrics. The applications includes map building, for example, the Google Street View, or the unmanned aerial vehicle-based sensing, or the mobile sensor network. Traditionally, those applications were modeled by the famous vehicle routing problem. The policies mainly falls in three categories. The first, based on time, for example, the first come, first served policy. The second, based on task locations, for example, the nearest neighbor policy. The third, based on task size, for example, the shortest job first policy. While those policies work for single customer system, they do not provide performance isolation for the multi-customer system. For example, in the table, we have two customers. The first customer has all the tasks arrive at time 0, while the customer has a periodic task arrival. If we are using a first come, first served policy, all the tasks of customer 1 will be served before customer 2, and customer 2 will be stuffed. Likewise, if we are using a nearest neighbor policy, in the case as shown in the top right figure, where we have two customers, the blue customer with the blue tasks and the red customer with the red tasks. All the blue tasks happen to be closer to the real vehicle than the red tasks. So all the blue tasks will be served first. Since the cloud computing has a very good notion of performance isolation, we are thinking about borrow the concept of the virtual machine in cloud computing to create performance isolation in this system with tasks arriving in time and space. In the cloud computing, a performance isolation means the resource consumption of one virtual machine should not impact the promised achievement of other virtual machines on the same hardware. We are thinking about to borrow this concept of virtual machine and create a concept called the virtual vehicle to create performance isolation. This is the concept of the virtual vehicle. To a customer, a virtual vehicle with virtual speed VV is exactly the same as a real vehicle with the same virtual speed. When the tasks arrive to the customer, it will form a queue in front of the virtual vehicle, and each task will have a virtual departure time according to this queue and the virtual speed. The provider's aim is trying to finish all the tasks before the virtual departure time. Thus, the virtual departure time behaves like a deadline for the provider. So we call the virtual departure time the virtual deadline. How the provider realizes the virtual deadline is of no concern of the customer. For example, the provider can use a real vehicle exactly the same as a virtual vehicle, or it can migrate the virtual vehicle to another real vehicle that is closer to the task to be executed. The concept of virtual vehicle and virtual deadline create a soft real-time system. Thus, we can use the common metrics such as the tardiness and delivery probability to measure the performance isolation. Low tardiness and high delivery probability indicate high performance isolation. For example, the delivery probability measures the percentage of tasks that has the actual completion time earlier than the virtual deadline. Our Voronoi allocation policy ensures that every real vehicle is also a queue. We will talk about this more later. We show that the provider can support a given number of virtual vehicles with significantly fewer real vehicles. We measure this gain by the number of virtual vehicles over the number of real vehicles. This gain happens because of two reasons. The first is from multiplexing gain. That is, a customer may not fully utilize her virtual vehicle. The other comes from the migration gain. That is, the provider can migrate the virtual vehicle to another real vehicle that is closer to the task to be executed. Of course, this migration will generate a migration cost. We show that the migration cost is bounded. So to sum up, as a result, a virtual vehicle performs as well as a real vehicle with high performance estimation, and the provider can support a given number of virtual vehicles with significantly fewer real vehicles, while guarantee high performance estimation and bounded migration cost. The allocation is called the Voronoi destination. Basically, we divide the whole area into M sub-areas and allocate each of the M real vehicles to each of the sub-regions. Inside each sub-region, that real vehicle will run the scheduling policy. We design three scheduling policies. The first is called the earliest virtual deadline first. This is for the case when task size is known a priori. The other two are called the earliest dynamic virtual deadline first and the credit scheduling policy. These two are for the case when task size is not known a priori. We also prove the optimality of the earliest deadline first in the case that it achieves minimum tardiness. We also design the worst case arrival process, which is called the eta arrival process. We prove that under the earliest virtual deadline first, the eta equals 1 process achieves maximum tardiness among all the renewal processes. The virtual vehicle is fully utilized under the eta equals 1 process. Thus, the gain observed is migration gain only. Since migration gain is unique to this spatial cloud, this research mainly focuses on migration gain. This figure shows the performance estimation based on tardiness and delivery probability with different number of real vehicles and gain value. We can also see that the migration cost is bounded. This figure shows the contours of the performance estimation based on tardiness and the delivery probability with different number of real vehicles and gain values. The top two figures are the cases when the task size is 0. The bottom two figures are the cases when the task size is 1/4 of the average travel time. We can see that the provider can host a given number of virtual vehicles with significantly fewer number of real vehicles. For example, to guarantee a tardiness of less than 1%, the provider can use only 100 real vehicles to host 750 virtual vehicles. This figure shows the performance between the three scheduling policies: the earliest virtual deadline first, the earliest dynamic virtual deadline first, and the credit scheduling policy. We can say that the EVDF achieves higher gain than the eDVDF, and eDVDF achieves higher gain than the credit scheduling policy. Here are the conclusion and acknowledgements. We conclude that, first, the migration gain is significantly high while guarantee high performance estimation. Second, the migration gain increase with the numbers of real vehicles while guarantee the same performance estimation, showing economy of scale. Also, the migration cost is bounded. Fourth, the virtual vehicle concept works best when the task sizes are small and the vehicle spends more time traveling to tasks than it does standing still. Fifth, the EVDF scheduling policy has better performance than eDVDF, and eDVDF has better performance than the credit scheduling policy. This research is supported by the National Science Foundation and the National Research Network RISE on rigorous system engineering. Here are the references. Thank you.